Alright, let's Hey. Hey, Mas.
That dude wants to learn about polymer thermodynamics.
All right, everybody sit down. We're gonna get the class started. What?
She's gonna be pissed. She's gonna. It's not gonna be good.
Yeah, that should be bad.
Okay. Okay, we can get started for today. Looks like the early side haven't have everybody there yet. I cannot hear you. Yeah, likely.
Yes, they're not here yet. I believe they're coming, but I don't see anyone.
Okay, I'll get started. They can follow up. I'll send an email, make sure they show up in class on time. Okay, so good afternoon, everybody. We're going to start this afternoon lecture. I'll keep it straight and simple. So last class, we started about entropy of the mixing. We talked about what is lattice theory when you mix two solvents together, what the entropy change before and after mixing. Well, that's not that's not the whole story about how the mixing effect will happen or not, because we missed the opportunity to talk about the enthalpy change before and after mixing. So for today's lecture, we will start to talk about enthalpy of mixing. Specifically, we want to discuss about the volume, assuming there's no volume change before and after mixing, how does molecular interaction changes with each other, okay? So before I start my lecture, we're going to first talk about we're going to talk about a concept called cohesive energy density, which is shown here. Can anyone think around that when you pull two molecules apart, what kind of energy change you would need to have? There's a lot of molecular interaction happening. You know, you have dipole-dipole interaction, You have Lennard-Jones interaction. If your material is charged, you can have a charge interaction between different species. So what would be the change happening if you consider a volume of the liquids shows here? You have dots more or less connected with each other to more gas states. So gas, we assume it's basically very diluted state of molecular. So you don't have much interaction anymore because the molecular is so far away and they're so sparse that way, so there's nothing in between. So how can we describe this energy? Because this is important. In the solution mixed states, if you mix solvent A versus B, let's talk about here. Think about, again, I would like to draw a box with molecular A, and B is the second molecular. Hold on. We're going to have a different color. Oh, I got some. That's very strange. Looks like connector is old and Asian. Well, the aspect ratio gets better, but the color is getting strange. We don't need a pink color. Well, if it's still not addressed, we can ask the school to fix it after class. Hold on. Well, it doesn't seem something I can easily address. All right, we can fix it later in the class. Coming back to this topic, when you consider mixing two of the moleculars, we need to consider a concept called cohesive energy. What this means is if you have two kind of solvent moleculars in the solution states close to each other, and if you make a gas out of it, you're just boiling it up, you basically pull the two molecular apart. And the energy cost to pull them apart is basically intermolecular interaction force. Okay? We can define this generic term in terms of number of energies we would have. We can just call it, define a parameter, tell you what is the interaction force you would have in these two cases. This doesn't seem useful anymore. Let me pull the board up. You have moleculars interacting with itself. Why don't we call this interaction A to A molecular as W11? One means species of solvent 1 interact with itself. That's for a single molecular, what kind of energy you need to vaporize a solution to gas state, okay? So that's called W11. And how about in a second case, we can define the cohesive energy between molecular 2 versus 2 is just called W22. So you have two kind of interaction. Before mixing, we have a lot of AA and BB. And after mixing, you would have a big basket. You're going to have A swimming around, and you're going to have B swimming around. And now what kind of interaction we would have in this case? You're going to introduce a new interaction called AB. Right? AB. Oh, we call it 1, 2. Different interactions. So if A is a male, B is female, so that's male-female interaction. And that's male-male interaction. That's female-female interaction. It's kind of weird while I'm saying these interactions, but you can imagine. In this box, what type of interaction you would expect? Is everything going to be W12? No. You're still going to have molecular A interact with A itself, right? So that's a reason we now need to consider what it is. How can we describe different state of AB and A plus B in terms of enthalpy? Because we basically use the cohesive energy to describe this enthalpy changes before and after. Okay? Because this magic term called cohesive energy is basically one term can describe all these conditions. And this enthalpy energy tells you how much energy you fully separate these two molecules from the closed state where they have cohesive energy to totally separate it apart. So how can we do that? And it's a parameter would depends on how many molecules you actually have there. So if you think about, if you have a lot of A where we start off, it would depend on number of the pairs we have. So each A and A would have a certain interaction, okay? So how can we describe this? If we assume the number of molecules is N1, this is N2. N is just a number of molecules. It could be a random number from 1 to 100. So how can we calculate the interaction force? You know? How can we understand interaction force in this A and A state? We know the number of molecules there.
M1 times W11.
N1, so let's call it enthalpy state for H1 will be, you say number of N1 times W11, right? Close. It's not exactly there. Why? Because we sort of counted the molecular interaction need to be counted for a pair of molecules, not just one. So it should be 1/2 divided by that. Okay? And this also depends on another parameter called lattice parameter. Let me define this parameter just for you. Z is lattice parameter. What this means? If we consider now all your molecules is fall into this boxes. If we start to feel this is solvent A, for each molecule, it has different number of neighbors. And if we assume this cohesive energy only happens when your molecular is close with each other, then we can see for this given x, you would need to consider cohesive energy with its closest neighbor of this. We can call it John, Mark, Eric, Daniel. Okay? So all of them are the same distance. So you need to consider when you pull this x out, or the John, Mark, Eric, and Daniel are going to start to pulling it back. Because this force is sensed by everywhere. But we don't consider a long distance. So we do not consider any interaction from this to that. So in a real world, you can consider how your molecular packs. These can be, think about a Rubik cube. If you have something in the center, you have actually 6 nearest neighbor, which has contributed to this called lattice parameter z. Okay? And z is just a constant number. We need to consider what lattice we put there. Okay, now does it make sense for everybody? What this means enthalpy for initial state for solvent A before mixing. So this is a before mixing, okay? You certainly don't have the your entropy state is 0 because we know there's only one way you can arrange all the moleculars in a given box. It won't change. It's just one state. But enthalpy is different. We just need to count how many moleculars is interacting with its closest neighbor, and we need to count what's the interaction force for this given molecular with its closer neighbor. Question so far? Anyone? No question? Good. Now I'll give you guys a short question for what is H2 for the initial state for the B molecular. You know that the number of them is N2. Interaction force is W22. Someone.
1/2 M2 W22 times.
Oh, Sam, you got all the questions right. I need to give you when you play games, there's a concept called cooldown.
Cooldown?
Yeah, we need to give you a cooldown time for 10 minutes. Because you're answering all the grid. You know what is cooldown? When you execute a skill, it's so powerful that none of us can have the question now, right? No, I'm just teasing. So how about then after mixing? This is a little bit trickier. After mixing.
Ratio of the two.
So how do we consider after mixing? So for the first half of the class, we're just gonna understand this question about H12. If we solve this, we know definition of delta H is after mixing minus the initial state. After mixing, so we only need to get this minus H1 minus H2. So we got delta H. And everybody got that what we talked about last class is the delta S, the entropy change, which should be K right? And we know this is always negative, so what we need to do is just to address what delta H. Okay, now I think this is your professor now has there's magic power. I become a molecular and stuck here forever. I cannot get out. And the monogon, which is the monster, also turn you guys into these molecular. So we're stuck in this classroom right here forever. How can we consider the interaction in this case? How many interaction we would have male students interact with male student, and how much chances female versus male, then how much of you is female and female? So, how can we consider this question? Because we know if 2 female students, that's going to be interaction of W22. We just need to count how many female students in the classroom and how many chances you can sit next to a female student. Let's think about this classroom. I ask everybody, stand up, random, move around, then sit down again. So this is like more or less the case over there. So, I wouldn't do that. That would be too much. You guys want to do that? No. It's okay, right? Somebody, please, make a suggestion.
Know the concentrations of each?
Haha! Why concentration of each matters?
Because that will determine how often you interact with yourself or
Right, right. Probability is depend on volume fraction of female student and the male student. So in this class, if we have 1, 2, 3, 4, oh, Sonia is on leave today, so we only have 4. So 4 out of 12, 13. That's the chance of if we randomize class. The chances of if it's dark room, your chance have another student sitting next to you is female is 4 out of 13, right? And if you have a male student next to you, we assume the number is infinitely high, so you don't need to take yourself out of consideration in the solution. So that's direct proportional to the concentration. So how do we describe this term? We need to consider, again, half. Let's first consider M1. We're still going to keep the number of lattice parameter because it doesn't matter which part you touch. X2, W12. Can someone explain what this equation tells us? Suravi. Yeah, okay, let's.
Number of molecules of A
Yes?
corresponds to that. How
Yeah.
they interact with each other or B.
Yes, right? So X1 is volume fraction of molecular N1. If everybody remember, X1, let me write here. X1 by definition is that's just volume fraction, okay? Easy, straightforward. M1, just 1 second. M1 chances of hitting itself is probability is X1 because that's a volume fraction, right? And if it's hit itself, it's going to have its W11 interaction. If it's me, the other molecule, it will be W12 interaction. Straightforward, easy. Is that it? Or did we miss something?
You have to do the same thing with M2.
So we need M2, Z, and how do we write this? X1?
X2.
X1 multiply.
W22. 1, 2.
First is 1, 2, because we now start with M2, right? Then plus. Okay. Cool. We now understand what is the interaction after we mix them. If we define just a very generic 2 terms, what is it? W11, W22. Cohesive energy, you need to pull A molecule versus itself apart. 2 is pull, 2 of the solvent 2 from the solution stay very much apart. And once you mix them, we start introduce the interaction with 1 and 2. It's a little bit abstract for now. I kind of agree with everybody that W11, W22, what a specific number we put there. There's a Polymer handbook here, you can actually look it up. Cohesive energy for all kind of different moleculars will give you how much easy or harder force you need to pull 2 of the molecular parts. If everybody remembers, there's a saying, if you want to choose a solvent, they call it, there's a solubility parameter. Everybody remember that? Solubility parameter is directly related to this cohesive energy. We won't talk too much, but they're related, they're proportional, okay? So, any question for this one, Mustafa?
So in this equation, for each component, we have contribution from this component and the contribution from the other component from the total, correct?
Yes.
In each. So we have 2 parts.
We have 2 parts.
Yes.
That's
so
where
one
you...
for component A and one for component B, and the one in the middle is from the other component from the total.
Yeah. Yeah, so as I mentioned, so now let's have one more pretty hand drawing from Professor Gu explain to you what's going on. Let's use dot and circle. So what do you guys want? This may be circle, circle. So if you consider this one, in this, z actually equals to 4 because there's 4 nearest neighbor. So we call it, what we define there is basically lattice parameter. In this case, lattice parameter is 4. Now, imagine this is me. I need to count interaction with this one, which is W, let's call it, this is 1, this is 2. This is W11. There's another neighbor, it's going to be 1, 2. This is another 1, 2. This is another 1, 1. So this only happens for this one. Now we need to count for this x again. We need to do the same. So if you count everything together, it will be generally summarized by this. Make sense?
Yeah. So is the cohesive energy, the molecular force, the sum of all of the interacting forces between AA?
Yeah.
Or is it?
It's
not the
some.
average, it's the sum.
It's one special case where you only have one single molecular A, one single molecular A again. And think about where now is in the solution state. So it's single molecular interaction. Somebody, can you help? Yeah? So now, if you give the system energy, they will start to separate.
Right.
Let's say in the case of you heat them up, they become gases. Now they're far away.
Right.
So the work you need to separate these two is basically called cohesive energy. Okay? So now if I have a water bottle, there's tons of molecules there. Now we need to count all the interactions, which will give you that. Okay? So as you can say, if I need to boil a bottle of water, it depends on how much volume you need to have. If it's a bigger volume, you cost more energy to boil it up because number of molecular is more, there is more number of interaction. Can you?
How is determining the lattice parameter?
Lattice parameter is basically a general definition about how your molecular pack. In 3-dimensional packing, people assume it will be Z would be about 6. In the case here, we basically show it's a grid where you have 4 nearest neighbor. But Z depends on how we consider a lattice. There's also a lattice you can consider. What if we have triangle lattice? Then you have 3 different nearest neighbor. It's kind of awkward. So most of the lattice theory is based on square. And in real case, we consider three-dimensional, where there's like a Rubik cube, so you have one in front of it and one in back of it. So Z is equal to 6. All right. It's late afternoon, and some student is yawning, so I cannot do math on the board. I will make it easy, just to write down the answer. Delta H, what this will be. We have this parameter. We have this parameter, H2, and we have H1. If we add everything together, what we would get is going to be M1, N2. I'm skipping some step in the middle, okay? This would be the final outcome. So the delta H, the changes in the enthalpy before and after mixing, depends on, we know Z is a constant. A lattice parameter depends on much, right? N1, N2 is number of moleculars in the system. As you can see, this is the total number of moleculars. This is number in 1. This is number in 2. We can play a few numbers later on to show you example. But if the number is fixed, it wouldn't change either. The most interesting part is actually in this part. The changes in the enthalpy strongly depends on the molecular interaction in W12. The interaction between cohesive energy between molecular case A and molecular case B, minus half of the W11 and half of W22. So it's basically average of A and B before the simple mass. So now the enthalpy of mixing is basically, can be defined as a very simple term, because this is very hard to memorize and remember. So to make things easy, we can define a new term called Flory-Huggins parameter. Okay, this is where the Flory-Huggins parameter comes into play. How do we define this? This is not x, but chi, and probably the most important parameter you would learn in polymer physics field. Okay.
Wait, so we were just using x before?
No. This is the x, but this is chi. Let me write it more dramatically.
Nice.
Enough? Everybody knows? Now this is a chi, and I'll try to keep in my mind. And we can define chi equals to z kt W12 minus 11 and minus 22. And we just gonna explain what's going on and why we need to define this chi term. Physical meaning of the chi, as we can see, kt is a constant, z is a parameter, is also a constant. So chi is a parameter, tells you what to be the cohesive energy before and after mixing. So chi, if this parameter is larger than 0, what's the physical meaning of it? Hey, anybody?
1, 2 is greater than 1, 1.
Yeah, I agree with that.
Is that right? No, chi larger than 0 means no. This should be the other way. Chi larger than 0 means this term is larger than 0. Oh, right. No. It was right at the beginning. If sometimes hesitating, most of the time I am wrong, okay? So what this means is after mixing, the interaction parameter will be larger than average of what you have begin. And we can have the other cases where chi equals 0 and chi minus 0. What's the benefit of doing this? Because chi now becomes a very simple term to describe what the enthalpy change. Let's look at this. I'm just going to write to tail of it, okay? This will now becomes, this term is basically already become a large parameter, right? This is basically highly related to the chi. This is equal to chi RT. So you would only left with N1, N2, N1 plus N2 multiplied by chi KT. Or if I want to simplify this, I know if I added two components together, this is basically total number of molecules in 1 and 2 and chi KT. Did we learn what delta S is? We did last class. Did we learn what delta H is? Yes, we do. If we are playing Legos, this will be equal to the last step of assembly Lego, which is you now assemble all the H and you assemble all the S. Let's put them together to get delta G. Everybody exciting? I am. Let's get delta G for the molecular system. That will define as what's a lattice theory for molecular mixing.
That's a good question.
Yes?
So
Mia? Yep.
in the last equation you wrote every there were molecules of 1 and then there were molecules of 2 over just molecules, that's the total number of molecules.
Yeah.
Okay. And then also I'm curious why in the expression just before that you do M1 times M2.
It is M1 time.
Yeah. No, I know. And I'm just wondering why isn't it just M subscript like 1 plus 2?
Ah, how can we get here? Right?
I'm just
Oh, how do we get this part?
sorry. Maybe I'll ask you after class.
No. Because I didn't explain it.
Well, I just think.
Right? I didn't explain. I said this sentence in the class. It's kind of afternoon, everybody is sleepy, so I'm going to do the math for you. So that's what we skipped actually.
Okay.
So if you add in what we talked about, what is H12 and minus H11 and minus H22, this is what you would simplify.
Thank you.
Okay? Everybody following? Easy cheesy. Afternoon is not a good time for math, right? So delta G free energy term we know the S, we know the H. This would be Okay, so there's two definitions we're going to talk about. Let's first talk about the easier one. So this is actually for the whole system, because we have how many number of sites, how number of interactions. There's also a way to better define per lattice site, because we know if we divide the top by number of lattice sites, which is m1 plus m2, we can basically get delta gm equals RT. Basically, this becomes x1 log x1 plus x2 log x2 plus, I think this I got wrong, sorry about that, x1, x2, and chi. Lattice theory for mixing of two solvents, delta G. Whoever did this theory is a genius. Look at how pretty it is. It's so symmetric. Delta G equals x1 log x1, x2 log x2, plus x1, x2 multiplied by chi. Lena, any question?
Is it G subscript N? Or
Yeah,
is it double
G
What
subscript
does that
N.
stand for
This
again?
is just to tell you the delta G is free energy difference for the molecular lattice. M is just to stand for molecular lattice. Okay? So, what is contributing to the mixing of the free energy? That's a science question we had at the beginning of class. The most important question we want to know is if you're mixing well mix or not mix. There's a crazy YouTube channel called Blend It or Not. Heard about this? Probably some rich guy, they have so much money, so everything in new electronic, they buy it. It's actually a blender company. They would put it into blender, press a button, start. Actually pretty powerful. It blends iPhone very nicely. If you want to show an iPhone there, it's become pieces. It's great for time killing. So now we also have a blended or not for our moleculars. How can we tell it will blend or not? It's basically depend on if the G is smaller than 0 or larger than 0. If the top case, blended or not. Blended, right? In last class, we know what's this contribution? Is less than 0. And we actually did a mass calculation for this part. This is the entropy contribution. So that's where all the entropy comes into play. And if your material will blend or not, this half of the equation says we're always going to blend entropically. Your system will go into disorder state while you mix two parts of molecular. The disorder for the system will always go up. So this part now may or may not blend, because now it depends on if chi is larger than 0 or smaller than 0. Is if it's gonna 100% blend now, because this in enthalpy will be negative. Entropy is always negative, so combining two negative unless the universe is destroyed. Negative plus negative is always negative, so you're always going to blend. But how about if chi is positive? Will it blend or not?
We don't know.
We don't know. Depends on magnitude of the chi, right? If it's just a little chi, entropy contribution will overpower the enthalpy contribution, so you're still going to mix it. But if there's a large chi value, they will not mix. Right? So instead of having a very abstract term, chi is basically contributing a lot to if your material will mix or not. So if chi value is large, that means there's a lot of, listen to this word, very important for the whole class today. There's a lot of unfavorable interaction between two components.
If chi is large.
Yes. Chi large is bad for mixing. Very, very bad. Okay? So you want low chi for mixing, high chi for phase separation. And again, coming back to this topic, so you can see chi large means there's a lot of unfavorable interaction in here. How does it compare? Okay? So you can actually look up chi parameters for different components. You can get the chi value. For example, PMMA and polystyrene has relatively low chi value. They're more likely to mix. While PDMS and polystyrene has very large chi value. They are very unlikely to mix. That's the first part of today's lecture about for lattice theory for mixing. And the take-home message is you want to know where is entropy contribution, where we talked about last class, or these statistics, how we get to entropy from number of possible states, and we actually get individual components, right? This both are entropy contribution. And we also have enthalpy contribution, where we talked about today is where different interactions for molecular A versus itself or A versus B. So Ravi?
In the equation you've written at the top for the
Yeah.
delta GM and the equation at the bottom, what's the difference?
The one is per whole system, the other is per molecular site. So the difference is basically top divided by M. So this is a whole system. Well, this means number of molecules, volume fraction, number of molecular B, volume fraction, number of molecular A, volume fraction of B, and multiplied by chi. If you divide by M, this becomes x1, this becomes x2, this becomes x1 again. That's why this comes into play. And what does divide by n is number of sites. The whole, whatever we draw, that pretty box I draw, is number of n sites. Right? Total number is total of n lattice sites. And that makes the difference, because this way it's more easy to understand, but it will not change the delta G from negative or positive. It just changes if it's per lattice sites or the whole system. Or the other way I can describe to you, if we have $100 worth or $100 debt, if we want to spread to every student, that's pretty much equal to what it's describing is debt per site or per student versus the whole system. It will be different, but it won't change. You own somebody money or somebody own you money. All right, we take a 5 minutes break, then we come back to talk about what happens if it's B is now become a polymer instead of solvents, because we're now going to do something related to the polymer science and engineering department. We're going to have polymers in solution. Okay? Sounds good? 5 minutes break. We come back. It's like the trap for professors. Like I put a lot of these in my house for my kids. Now you got to trap me. It's basically
And free energy of mixing in your lattice, right? I'm just
yeah,
trying to understand
yeah.
that, like, this.
No, M doesn't mean anything. So there's a GM.
This here.
Yeah, I think it just mean the mixing energy.
Oh.
Mm.
So,
So the difference between these two, where are these dots for?
I don't know. It's just so I can write straight.
Uh-huh. So this is just what we define the delta G, generic, what the changes in the free energy, and this is M stands for.
That's what I thought I understood you say.
I think I maybe did it wrong. It just
Oh.
means mixing,
Okay.
and there is a difference in right. This, the second term is just normalized by different lattice sides, right?
Right. So that's just like dividing it by the lattice size.
Right, because then you kind of move these n1 terms to x1 and make
Yeah.
a very different.
Okay.
But overall, I think you got it right in terms of what the
think
physical
so, yeah.
meaning.
Yeah, I think I understand it. I was just curious because I thought I heard you say that it was delta G in the lattice,
Mhm.
but it's just this what
Right.
you wrote means delta G. Mixed.
Right, it's just two different ways to
Yeah,
express the same concept.
Okay, great.
Good.
What's that?
Okay, let's get started for the second half. There's two of the students coming back. Okay, we're gonna give you guys an example so then help you to get some real values what these would means, okay? So is everybody following up on the textbook about chapter 7.2 and 3?
Working there.
Okay, working there. I know you guys have the test today.
Yeah.
How was it?
Terrible.
Not good.
So bad.
Real bad.
That was aggressive. It's not the afternoon.
I think we should maybe finish the class 5 minutes early so you guys can have time to bit and get to the normal state. So let's consider an example of mixing 1 moles of cyclohexane and 1 moles of toluene. This example is given on the textbook, so you actually can just follow with me. You don't need to write it down, it's exactly the same one. It gives you what is W11 and W12 and W22 is. So W12 will be minus 1.08 And W11 will be, so you know what's the interaction force for different toluene? So this is toluene, this is hexane, and this is toluene and hexane interaction force. So first thing we need to calculate is what is X or chi. What would be the chi for the molecular system? We actually need to apply KT. Delta W is just changes in the cohesive energy before and after. Okay. So if we apply all the values in the solution state, Z actually turns to 10. And this is a little bit surprise to me, but I'm trying to understand it. It's likely due to how many closest neighbor in the solid in a given state you would be able to pack in the solution state. It turns out to be Z would be equal to 10, which means there's going to be 10 closest neighbor you need to consider. KT, as we know, this is the Boltzmann constant. Temperature, we assume it's 0. Room temperature is going to be 298 Kelvin. What does this mean? Chi equals to 0.24. Wow, I need help. What does chi equals to 0.14 mean to you if you see this number? Huh? Larger than 0. So it's positive. So the toluene and hexane actually don't like to mix enthalpically. Okay? It costs more energy to pull those molecular parts. Especially, I'm missing a minus, sorry. Especially for toluene, it's easier to pull away than hexane, where you can see the value W22 is higher. But let's see which one wins over. As we say, chi is just part of the game, right? So let's do a mass. I now consider RT, so we can just move the RT to here because it's a constant. Delta G divided by RT will be X1. What is X1? No, 1. 0.5, right? Volume fraction. Huh? What?
You said the same thing.
Yeah. Yeah. Anyone have a problem understanding this? No. Entropic contribution plus enthalpic contribution. Okay, so let's have a guess. Will it mix or not? How many of you think it will mix? Oh, 1 mix? 2, 3? Okay, how many of you think it will not mix? Oh, we have 2, and the last 3 don't know, right? So if you mix hexane and toluene, you shake it, will it mix? Why don't we next class bring some toluene and hexane? Let's try it. And see if it agrees with the theory. How much is this? So this should be 1.38 roughly. No, wait. What's the value for this? I don't think I get. So it should be minus 0.693 divided by 2. Right?
Yes.
It's the same value for this part. It's actually 3. And how about the enthalpy contribution? 0.06. If you get everything right, this should be 0.63 per lattice side. It will tell you it will mix. All right, whoever betted not gonna mix, the guy bet to mix a glass of beer. And whoever didn't bet don't have a chance to win or lose. Does it make sense? This is how we actually apply those lattice theory to know if your molecule will mix or not mix. But one of the tricks is you have to look up the chi parameter. And this is in Polymer handbook. You can search any two combination of material. If you don't know, there's also an empirical equation link the solubility parameter with chi. If you know the solubility parameter, you can calculate what the chi is. Okay? Waiting.
How did they initially calculate chi?
So they measured that. They don't calculate. It can be measured. So there's several ways people can measure chi. One classical way is measure using a scattering mass mix, and through some mathematical treatment, you can get out extract what's the chi for given two material. And you can actually start to build a database of what's the known material and to get what's the chi value. However, it doesn't work for unknown material. Let's say I made a totally brand new polymer that has never been reported before. Then you need to measure the chi. And swelling measurement, you can also measure the chi, as well as osmotic pressure. We're going to talk in next class. You can also measure chi. There's many ways. Pi is basically a parameter if you like each other or not. If chi value is high, there's no chance you're going to be good friends. If chi is negative, you're buddy-buddy, okay? Any questions so far? If no more, let's move on to what if now B become a polymer? You now have A is still the small, but B is a polymer now. We now can finally draw what are my favorite chain conformation. Oh, great! You have a chain conformation solution. What's the difference? Well, to consider this problem, we just go back to what we know. We consider entropy difference for the mixing and enthalpy difference for mixing. What I can hint you is enthalpy, we don't expect much difference. Although they're connected, right? You can think about B, polymers with degree polymerization equals to n, means how long they are, okay, and segments. We can consider the number of molecular again is going to be n1 and this is going to be n2. But we now need to consider the volume difference. In the last case, we basically say n1, n2, both of them occupy this one beautiful lattice. But now it's polymer, so we need to consider more lattice. Let's assume if we now have degree of polymerization n, now this occupies N2 multiplied by N number of lattice. Makes sense, right? Because each one you now have taken more space. Now we can define, instead of x1, with basically volume fraction, used to be as simple as n1 plus n2. Now we just need to define a new term called phi. Again, it's a volume fraction. For the first phase, for the small molecular volume fraction, it's going to be n1 plus, is it n2? Is it n2? No. Right, it's a trap. So it's m2 multiplied by n. Because the volume for m2 is now different. Even we mixed 1 mole of solvent versus 1 mole of polymer, because of degree of polymerization, your size of solvent, your size of polymer now goes up. So this is volume fraction of solvent, and again, this is a volume fraction of your polymer. This will be n2 multiplied by n divided by n1 plus n2 multiplied by n, volume fraction of the polymer. Well, if you actually consider for the mixture, there's quite little difference in delta S. The expression we had before will be also valid here. Think about number of how does connectivity affect our entropy. I want to pose this as an open question for the class. I want you to think about, ask yourself this question. How actually the connectivity changes number of possible states, and how does that affect the entropy of your system in the mixing? I'll give you a hint. Enthalpy doesn't change. So before and after, it's still the same. So we can use the same theory to describe it. So the delta H will be basically, again, it's going to be N1 phi 2 x, this is chi kt, but delta S will be different with before. Delta S now has influence coming from the connectivity. So the delta S actually will become k log phi 1 plus and I'll give you guys some moment to think about as part of the homework. You don't need to turn it in, but think about why the new entropy differences for mixing a polymer with a solvent have one additional term comes here. That's the only difference you have versus a regular solution lattice, okay? The connectivity made a difference. Degree of polymerization is here. I'll explain at the beginning of next class, okay? Well, everybody think I'm going to finish the class? I'm going to take another 2-3 minutes, okay? What are the impact of this N? What's the impact? Remember the little demonstration we did here? What's the impact? There's a huge impact. Entropy for solvent contribution in the mixing is still the same. It's going to be volume fraction, or we used to write x1. I just want to differentiate, so it's going to become phi1 volume phi1. Doesn't change. So solvents still behave like independently, very happy. But entropy contribution from polymer is different, because before mixing and after mixing, it's now reduced by a factor of n. Huge, right? So if you think about the other case where we talked about mixing toluene, hexane, now one part becomes a polymer, and we need to divide enthalpy contribution reduced by n. N could be a factor of 100 or 1,000. Your entropy contribution to the mixing is greatly reduced, tremendously reduced, I would say. Right? Used to be, this is about, entropy contribution is about minus, it's not on this note, but I'm trying to remember. Right? This is the entropy contribution, and enthalpy contribution is only 0.06. Think about this divided by 100. Not exactly 100 because solvents still hold, but imagine this is reduced by 100. This will be dropping to a similar level. Now, as you can see, polymer mixing is now not totally entropic driven. Polymer solvent still is, because solvent still have large contribution. But we can start seeing forward thinking. If you have polymer versus mixing another polymer, your entropy contribution for the phase A and phase B both going to have a hit by number of permutation. If you divide this by 1,000, you can see this will be larger than actually entropic driven. So your enthalpy start play a critical role in polymer mixing. Okay? I hope this part of give you some hint about what is Lattice series teach you about who is the boss at home. Is your wife or yourself? Depends. This may be the kid factor. Once the kids come to play, it's a different world now. Okay? So that summarized today's class. We kind of introduced we finished the Lattice theory. We touched a little bit about Flory-Huggins theory. I'll give a more detailed lecture once we fix the projector. Then we're going to wrap it up. So for the next class, we're going to start talking a little bit about osmotic pressure, and how does osmotic pressure would depend on some of the physical parameters we learn. Okay? If no more questions, we can finish up today's class. Mm-hmm.